12.2, what we're going to do is we're going to measure harmonic motion. We're going to measure it using certain parameters. Okay, and those parameters are things that will be somewhat familiar, things that you may have seen before. I know you've seen like frequency before in chemistry. You probably haven't seen anything with period or wavelength yet, or amplitude. But we're going to look at waves. Okay, we're going to take a look at waves and what they are. So in this section specifically, we're going to calculate the period and frequency of objects in simple harmonic motion. Let's take a look at some definitions first. What we're actually going to do. So amplitude is the maximum displacement from equilibrium. So for a pendulum, take a look up here. Here's equilibrium. The displacement would be measured in what units for a pendulum? What can I measure? For example, ready? Here's a small displacement. Here's a larger. Here's an even larger displacement. What units might I use to measure the displacement I'm using? For a pendulum. Depends on where it is. Good. So this would be what? How would you describe this compared to this? Okay, you could use meters and centimeters, but that's a little tougher because it depends on how long R is, right? If this is shorter, now it's less meters. If this is longer, now it's more meters. So that's tough. There's something we can use, though, in math that describes the pitch of something, not pitches and tone. Yes. Amplitude is the word, yeah, but I'm saying, see how units vary? I put at the end there? My question is, this is the amplitude for sure. And then I let go, and it comes back up to about its amplitude where it started from. But the question is, what units do I use to measure? Degrees. Very good, Kat. Degrees. So the units of amplitude for a pendulum are measured in degrees. This would be like 30 degrees, 45, 60, 90 degrees. And it's always measured with respect to equilibrium. Okay, so here's equilibrium. This is 0 degrees. If I raise this up to 30 degrees and let go, it will never go past 30 degrees because I know that there's some frictional loss. If I move my hand, I can get it from that, obviously, right? All right, that's for a pendulum for amplitude. What about a spring? How about a spring? So here's equilibrium, right? All right, so here's equilibrium right here, under this force. Now, I pull it down to it's at its maximum amplitude. How do I measure amplitude when it comes to a spring? Here's equilibrium. Here's maximum amplitude. What units would you use there? I heard a lot of answers, so I'm not certain who said the right one, who said the wrong one. Not newtons. Newtons is the amount of force you apply. Meters. Again, remember, amplitude is the maximum displacement from equilibrium. Displacement. Isn't that x? Isn't that meters? With a pendulum, it was a little trickier because the displacement was not a distance, yet it was an angle. So that's why Catherine told us to use degrees for a pendulum. Okay, but displacement for a spring is measured in meters. Okay, in meters or centimeters or some unit of length. Next, period. What is the period? The period is the time it takes to complete an entire cycle. So, ready? I let go of the pendulum. That's one period. Okay? I let go, and that's one period. So the full cycle, not just one wave to one side. A full cycle means it returns to its starting point. So for a spring, all right, for the spring, ready? I let go, and here, that's tougher to do. All right, so let me make it. I'll do it in slow motion. You let go, it rises, it comes all the way back down to where it started. That's one cycle. So the period is the time it takes to complete one cycle. One cycle. So for example, if you're driving your car and every minute the tires, well, that'd be really slow. Every second the tires rotated once, it would be one rotation per second. That's how you would describe the frequency. Now, frequency in physics class we use hertz. Hold on one. So for frequency here, we're going to use hertz in a minute. Now, the question is, what is frequency really? What is frequency really? Because period is easy to understand. It's the time it takes. But what's frequency really?
I just think like sound and so sound frequency,
Yeah, so
something like that.
for applications of sound, frequency is the pitch of the note. The pitch, so a higher pitch or a lower pitch, like something like a soprano versus an alto or a bass or something.
Is there like time it takes for one movement?
That's period, time for one cycle. But what's frequency is the question. Period is the time it takes for one cycle, but we want to know what the frequency really is. Yeah, how often, how quickly it occurs. So, let's give a quick sample. Which of these, ready? So, first of all, here's option 1, okay? And then here is option 2. Clearly, option 1 had a longer period length. It took a long time to do that. It took very little time to do that. Agreed? Okay. So, frequency is the opposite of that. It's the inverse of period, really. It's 1 over. So think about it, ready? Long period length means short or small frequency. If you count to 10, this is only going to occur a few times. Right? This is not occurring very quickly. So it's got a low frequency. Whereas this length here occurs really quick, right? So there's a pretty high frequency. So frequency is how often a cycle is completed in a given time period. Again, frequency is how often a cycle is completed in a given time period. So here we write the number of cycles per unit time. Okay, units are usually hertz. And I'll explain those units in a second. I'll explain what hertz really means. So we've got various units for amplitude, we've got seconds for our period, and we've got hertz for our frequency. Let's look now at our formulas so we can see what these units are. So these are 3 formulas that are given on your formula sheet, but they're definitely new variables. So the first formula says, and you should write these words down, that symbol is not W, that's called omega. Omega. It's a lowercase omega, really. It's a Greek symbol, if I'm not mistaken. Yeah, it's Greek, it's not Latin. So that Greek symbol omega means frequency. The first little looking W thing is called omega, and it means frequency. Now, in the denominator of that formula or function, or formula for this case, is tau. It looks like a T, right? Looks like a capital T down there. That right there looks like a capital T. It's called tau. T-A-U, not T-A-O, as in Taoism. Okay, T-A-U. Again, a Greek symbol, tau. That means the period length. Okay, and I'm going to use these words, so you need to be familiar with them. When I say omega, you need to know I'm talking about the frequency. Please don't say W in class. W's work or W's watts. We already enough W's. Okay, it's omega. When you hear me say tau, I'm talking about the period length. I'm not saying time. I'm talking about specifically the time between the beginning of the cycle and the end of the cycle. That is the period length. It is not just a given random time. What could you tell me now, based on this formula? What could you tell me? Well, clearly you can see the relationship, but let's start with that. What's the relationship between frequency and period from that formula, and why? What relationship exists between frequency and period? Good. They're inversely or indirectly related. Same word, of course. They're indirectly or inversely related. And that's obvious because it's 1 over. Right? Just like our formulas when you have something in the denominator. When something's in the denominator of a formula, it means it's indirectly related to whatever is outside the formula, omega in this case. Now, what are the units of tau? What are the units of tau? What is it? S for seconds, because tau is measuring the time period, so it's measured in seconds. If tau is measured in seconds, and we look at our dimensions in this problem, if we simply look at our dimensions for this specific problem, okay, look right here and write out your dimensions. We've got hertz equals something over seconds. Well, what are the units of 1? What are the units of pi? What are pi's units? Louder? Yeah, it's a constant. So what are the units of 1? Okay, so there's no unit on the top. So if there's no units on top, you just put the number 1 there. It's not an L, it's a number 1. So a hertz, the units of hertz frequency is really called 1 over seconds. But the name hertz is used so commonly that I want you to know. Again, this is cycles per second. Remember, frequency is cycles per second. And I'll point to what I'm referring to here. This really means 1 cycle per second. If this were 2, it's 2 cycles per second. It depends on what the frequency actually is. But hertz, by definition, are 1 over seconds as far as units are concerned. All right, so that's the relationship between frequency and period for any system. Now, after that, we specifically look at the period of 2 types of systems. And what do we notice right away? Make some comments about the next 2 formulas. I mean, something's got to be obvious. It's got to stick out a little bit. Yeah, they both use 2 pi and they have that square root. Okay? Why do you think they both use 2 pi? Take a guess. Why do you think they both use 2 pi? Yeah. We're talking about something that's cyclical motion, right? That is continuous. It's a wave that goes over and over again. Well, something that's moving in a circle is periodic. It's circular motion. That's where the 2 pi really comes from. It's the length around a circle with a radius of 1. Okay, it's the circumference of a circle with a radius of 1. Now, what do you notice though about inside the radical? What could you say about one that's not true about the other? Because both of these, right? For example, this is a mass on a pendulum with a length. This is a mass on a spring, and that spring itself also can have a length, okay, and a spring constant K.
Mass is not needed
For the pendulum, mass is not needed, which is very interesting to think about. Because if I add more mass to this, watch. If I take these, oops, I'm sorry, that rolled over. I think it's under curious. Oh no, thanks, man. So if I take these masses off of here, all right, and I pull this and let go, look how quick this ends. See how quick the period was there? It stopped very quickly. It damaged itself very quickly. The minute I have masses on here, stuff's changing. Look at my formula. If I look, isn't the mass directly related to the period? So there's more mass now, but what you'll notice is that this moves slower. The period length is longer. It takes longer for this to complete 1 cycle. So the mass is affecting the period length of a mass spring system. But here, believe it or not, I'm not going to prove this to you now because I want you to do it in your lab. It doesn't matter what's on the end of this. I mean, it does, but it doesn't. Like if you have nothing on the end of this, the string is not going to move as quickly because of air resistance. But if you have this wooden,
Is that a mothball?
I don't know, yes, this wooden object here, and that's just, they're made for these actually. So if you have this wooden object versus like a solid steel sphere instead, and you let go, they will both take the same amount of time to get back to the starting point, which is very misleading. You wouldn't think that at all. But the interesting part is that the period of a pendulum is only a function of what? It's what? Its length. Why does G not really matter? Because we are on Earth. Okay, if we did this on another planet, you could actually measure the gravitational constant on a planet with this formula alone. You can go to Mars today. Well, probably can't, but if you could, you're on Mars today. If you brought a pendulum and you knew the length of the pendulum, L. If you knew the length of the pendulum, L, and you measured the time it took for you to do this, you can actually calculate G from this formula. There are many ways to find G on any given surface or planet. Very simple ways. This is one of the ways. Since we're mainly on Earth, G is not changing. So take a look. Again, long period. Then I take the length, I shorten it a lot, and a much shorter period. Because the length and the period are also directly related to one another. Alright? How are we doing so far? Does it make sense? There's a lot going on with these ideas. Okay, let's keep moving then. Let's keep moving. One of these examples mathematically. Can I get someone to read for us nice and loud, please? Go for it, Jake.
A massive 20 kilograms is connected to a spring and oscillates in simple harmonic motion. If the spring constant is 35 newtons per meter, then determine the period and frequency of
So we've got a mass on a surface. It oscillates back and forth in simple harmonic motion. So we know it's going back and forth. Somebody pulls on the object, lets go, and it just sits there and slides back and forth. Now, really, with friction, the period lengths are going to be less than what you get as an answer. In think about that logically for a second. Okay, the period length is going to change as a function of how much friction there is. We're assuming there's no friction, all right? Our goal in this problem specifically is to find the period and the frequency of the system. What do we know? Give me some givens about this. Give me a given. Ed, give me one of the givens. Yeah, mass is 20 kilograms. We're looking at a spring system, so what else might we have? Which is? All right, so we've got those two quantities. With both of those, is that enough to find the period? Let's think about our formula. I think it is enough. Take a look. If you know the mass, and you know the rigidity of the spring, you can figure out how long it takes for one period to occur. So if you find the period first, you can then find the frequency after that. Go ahead and find the period first. Starts where it is, say, I don't know, let's say this is the equilibrium state, okay? Okay, so to answer Jake's question, the question was, what physically is the period length here? So imagine this spring was stretched so that the mass was out here now. The time it takes to, when it's released, oscillate this way and then come back to where it was and end up right here, that's one period length. So when this spring is let go, it goes like this and then it comes back, that's one period. It's the same thing as the pendulum that goes both directions for that. All right, so if that is the period length, what is the frequency? What's the frequency if that's the period? Yeah, 1 over that. What do you get as a number, Paul? 2, 1? Because I'm writing it like a W because there's really no other way. I mean, a W is really this way in Arabic. This is, I mean, it's really, you know. Well, okay, some textbooks, I think your book might even use F for frequency, but F is used so in engineering and science, you're the ow. Okay, guys, stop. All right, so again, if you know the frequency, you can get the period. If you know the period, you can get the frequency. Just do 1 over every time. So if you know the frequency of a problem and you want the period for some reason, just do 1 over that. Here we knew the period because we determined it, and to get the frequency, we did 1 over that. So it's always 1 over. It's always 1 over from that formula. Ed, guys, come on, focus. The second example says, determine the length needed for a simple pendulum to have a frequency of 2 hertz. 2 hertz. Okay? Determine the actual length needed. So start by thinking about what you know, what you're looking for, what you're given. It's not an obvious process here. What do I know?
The W of whatever. No, you say.
Omega equals
2 hertz.
2 hertz. Anybody watch, was it on Simpsons, the Hertz Donut? You don't know Hertz Donut? You go up to somebody and ask them, you want a Hertz Donut? And they say what? You punch them and say Hertz Donut. Anyway, Hertz. Don't actually do it to each other. That was like, when I was like in high school, that was like a funny thing, believe it or not. I know, things were not really funny back then. All right, so we are trying to figure out what the length is of this pendulum. What else do I know? I need some other information. What else do I know? 1 over? Yeah. Okay, we technically know the period length because it's 1 over the frequency. And since the frequency is 2 hertz, it's 1 over 2 hertz. Okay? And hertz are 1 over seconds, so this becomes, ready, watch what this looks like. 1 over 2, and the units of hertz are really 1 over seconds. These are the units right here. So you end up with 1 over 2, meaning a half of a second. Okay, it follows this way. So you have period length, 1 over 2 hertz, but a hertz is really 1 over seconds. If you divide by 1 over seconds, it takes seconds and puts it up in the numerator, which makes this 0.5 seconds, or just a half of a second. So as a result, if we know the frequency, we know the period length. Now, we have the period length, the frequency, and we want the length of the pendulum. We want the length of the pendulum. What equation should we use? Good. Root L over G. Exactly right. And take a look at your formula here. Now you see why we came up with the tau value, the 0.5, because that's going to go right here. So the frequency we're not really using directly here, we're using it indirectly. There's no variable for frequency in this formula anyway. So what you're doing is you're using the frequency, from that you're determining the period length. You know gravity on Earth is 9.81, you know 2 and pi, so your goal is to find L. Now, in the other section, a lot of people made mistakes solving for L algebraically and then also plugging the calculator. So please follow along with me now, because I'm telling you, a lot of people made mistakes on this one. So to solve for L, solving for L is the first part. Then I can plug in the numbers I know. But for now, how do I solve for L algebraically? Give me the first step, Ed. You could. You can definitely start by squaring both sides, but if you do that, you need to remember to square the 2 pi and the radical L over G. So you could start by doing this. Oops. That's one way to start it. Square everything, because everything is a product, right? You see everything is a product. So if you square this whole side, you got to square 2, square pi, and square this whole thing. Squaring this whole thing is L over G. Squaring 2 is 4, squaring pi is pi squared, squaring tau is tau squared. That's definitely one way to do it. You can do it another way also. What's another way? Okay? Okay, but what would you multiply though? By using, from the red line or from the blue line that we started with, you're talking about? From the blue line you could, but you have to multiply by root G over L. But remember, we're trying to find out L, and L is already in the numerator, so I would leave it. I wouldn't get rid of it with the reciprocal, but that is one way you could approach it. You can definitely do that. What's another way? You could have started off by dividing by 2 pi, and then getting rid of the square root. That works also. So let me show you the alternate approach that Marianne just mentioned. Dividing by 2 pi, you get this. That's what you would get. And then you would have to square that, which in essence would give you the same thing, right? Let's do both of these methods. We'll do this one in red and the one in black. In black, if we squared both sides, we get tau squared over 4 pi squared equals L over G. Well, it's the same thing here if we just divide by 4 pi squared. Divide both sides by 4 pi squared, giving you tau squared over 4 pi squared equals L over G. So either way is the same answer in the end, but some students do better squaring first or squaring after. It's up to you. You decide what you'd like to do. But in this stage, remember, we divided by 2 pi, then we squared this side, making it this, squared this side, making it this. But in the end, same thing. Now here is the last step, obviously multiply by G, that's easy. To get L by itself, multiply by G on both equations. So put a G up here, and that G is gone. Okay, or put a G up here, and that G is now gone. So that's what L is. G tau squared over 4 pi squared. But the mistake I kept seeing was this. And this is the mistake I mean with the calculator part. This is definitely your answer right here. Okay, that's the answer for L. G tau squared over 4 pi squared. What do you think people are forgetting to do when they put it in their calculator? What was the one? There are 2 mistakes that people are making actually. What's one of them? Give me one of them, Kat. Yeah, so here, the square is only on the pi. It's not on the whole denominator. So some students were putting divided by the quantity 4 pi squared. We already squared the 2. Remember that 2 earlier for the 2 pi? Yeah. When we squared 2 pi, we got 4 pi squared. So as a result, we didn't have to worry about squaring this again. This pi is squared, but the 4 is not. What's the other mistake that people might have made? There's one other mistake. You're dividing by a product, aren't you? Isn't the denominator a product? So when you divide by a product, what do you have to remember to do with the denominator? Parentheses. So when you're typing this in your calculator, you should type in 9.81 times tau was 0.5, so 0.5 squared divided by parentheses 4 pi squared. Like that. That's what it should look like in your calculator. As long, the numerator is in parentheses. The calculator knows to do the numerator first. It does this work first. Then it divides by this whole quantity. If you forgot in parentheses, it would divide by 4 first, and then it would multiply that answer by pi squared, which is not what you want. If you put the square in here, it would square both of these, which is not what you want. Okay, what do you get for a length? What was it? Yeah. That's right. God bless you. 0.062 meters. So, folks, let's see if I'm right. Let's see if this is, I guess, theoretically correct. There's going to be errors distance, so you'll go off. But 0.062 meters, what is that? In more tangible units. What is it? 6.2 centimeters, right? So let's take a look. Let's measure 6.2 centimeters on here. Ow. So, here's 6.2 centimeters, okay? From where my finger is attached to this pendulum. Now, earlier we were told that the period length would be 0.5 seconds. 0.5 seconds. Anybody have a stopwatch on their phone that can, or on their iPad or something that can time for us?
Yeah.
All right, we're going to time at least five of these periods. And then we'll divide by 5. So we're going to do 5, okay? I'll tell you.
Wait, so every time I have to stop it once okay. Alright. Wait, I don't know.
I'll tell you when to start and stop.
Okay.
Ready, set.
Oh, wait.
Go.
Okay, alright, I got it now.
Ready, set, go. Stop. What'd you get?
2.7.
Perfect. Divide that by 5. 2.78 was the time it took for 5 cycles. Divide. What? That sounded actually pretty close. What'd you get? 3.3. What'd you get?
I got 3.4.
Alright, well, around 3 seconds. So, if you divide that by 5, you're going to get 0.6 or 0.5 seconds in between there. What'd you get? 0.5? 0.56. The time it should take should be a half a second for one of these. Okay, so again, what's happening as this occurs? Air resistance is affecting it. So notice the amplitudes are getting smaller and smaller. So when we measure the time is going to be off a little bit. So in your lab, when you do this, it's not going to be for 5 centimeters because this is a little bit tricky. The length is going to be around 15 centimeters. Okay, so you're going to be measuring the time it takes for this, okay, to occur X amount of times. Does that make sense?
Yes.
All right, have an idea of what you're doing? Now, let me just see if I want to go through anything else first. Hold on. I'm going to